Hello viewers, welcome to this next lecture on the NPTEL MOOC course on mathematical portfolio theory. So far what we have been looking at in the bond portfolio optimization in the framework of finding out matrices or measures to ascertain what is the risk associated with the bond from the point of view of its price movement resulting from change in the interest rate. And so far we have looked at what is the pricing of the bond yield to maturity, and we have talked about duration, the properties of duration and what is going to be the duration of a portfolio, and the concept of immunization or risk management in case of bond portfolio by matching of duration. So, we continue our discussion in today's class by extending this to the notion of convexity, and then we will further discuss this concept of convexity in the context of a portfolio, and then we will see this in the framework of the percentage change of the bond prices, and then we will look at a couple of example to illustrate this notion of immunization, which is the most basic notion in case of risk management for bond portfolios. So, accordingly we now start this lecture with the concept of convexity. So, recall that the mathematical notation of convexity of a curve, it means or is interpreted as the rate of change of the slope of the curve. So, more formally in the context of our discussion, I will start off with the definition as follows, that in the case of bonds, the convexity is defined as C is equal to 1 over B r into d d r of d b d r, and this is 1 over B r into d square b d r square. So, the presence of this term B r in the expression and also this B r, this as opposed to only the rate of change of B r for convexity. So, for convexity normally I would just look at this term, but there is an additional term B r in the denominator. So, this will be motivated, that is the reason why you have included this term B r in the subsequent discussion. Now, recall that dB dr, we have already got the expression for this, and what was this? This was summation of C t and the derivative with respect to r of 1 plus r raised to minus t. So, this derivative becomes minus t into 1 plus r raised to minus t minus 1, t is equal to 1 to capital T. So, from here we therefore get that C is equal to 1 over B into d square b dr square, and this is going to be 1 over b into 1 plus r square into summation t into t plus 1 c of t into 1 plus r raised to minus t, t is equal to 1 to capital T. So, basically C is 1 over b into the second derivative, and the second derivative here is obtained by taking the derivative of this expression here to eventually get this expression for convexity. So, let us look at the convexity in case of a bond portfolio. So, we consider a bond portfolio comprising of capital N number of bonds, and let the number of units. So, the setup is the same as that of duration in case of a bond portfolio. So, accordingly, let the number of units of the kth bond in the portfolio of this n number of bonds be denoted by n k, with the corresponding prices being denoted by B k of r, and for k is equal to, remember there are n number of bonds. So, k equal to 1 to all the way to capital N. Then the value of the portfolio is given by B p is equal to summation n k B k of r, k is equal to 1 to capital N. Right. So, this is basically the value of this bond portfolio. So, now what you do is, if you want to find out the convexity of this bond portfolio, so accordingly what you need to do is, then we differentiate B p twice. Remember, this is the definition of convexity. So, we need the second derivative with respect to r, and then divide this by B p of r. We obtain the following. So, what do you obtain? We get that d square b p over d r square is summation k is equal to 1 to capital N n k d square b k r of d r, and this implies that if I want the definition of convexity, so I have to divide by B p. So, 1 over B p d square B p d r square, this is going to be summation k is equal to 1 to n k into B k of r divided by B p of r multiplied by 1 over B k of r into d square B k of r over d r square. So, basically we are just dividing both sides by B p and then multiplying and divided both sides by B k of r, so that I can recover the weights. So, this implies that, so this term here on the left hand side by definition is the convexity of the portfolio, and this term here is the convexity of the kth asset, and this, as before, this term is the weight. So, this is going to be W k C k, the summation of this k is equal to 1 to capital N. So, thus the convexity of the bond portfolio is going to be equal to the weighted sum of the convexity of the bonds in the portfolio. So, here C p is the convexity of the bond, C k is the So, Cp is the convexity of the bond portfolio, Ck is the convexity of the kth bond, Wk which was Nk Bk of R over Bp of R. This is the weight of the kth bond in the portfolio, and finally, you observe that summation W k is equal to 1 to capital N. This is going to be summation N k B k of R k is equal to 1 to N over B p of R. This is B p of R over B p of R, and this is equal to 1. So, the weights defined in this way is again satisfies the condition that the sum of the weights is equal to 1. Okay, what you do next now is we will now that you have defined duration and convexity, the next thing we will do is now that we will do a connection of duration and convexity. Okay, so as before we considered the same setup, and suppose that the bond prices is a function of R and is given by B of R. Now, let a small change dr in the interest rate result in a corresponding small change in the bond price. So, if a small interest rate change of dr results in the change in the bond price, then what we have? Then the percentage change in the bond price is given by the following. So, your original bond price was B r and the new bond price is B when the interest rate is R plus dr. Remember, the interest rate changes by dr. So, the change in the bond price as a result of the interest rate changing from R to R plus dr is given by B of R plus dr minus Br, and according to the proportional change will be the ratio of this Br plus dr minus Br over the original Br, and this is nothing but I will have B in the denominator, and on the numerator I will have the change delta B over B. So, this basically gives you the percentage change in the bond price. Okay, now let us focus on this particular term. So, and remember that we had said that the dr is a small change. So, accordingly we can make a Taylor series approximation, and accordingly we expand B of R plus dr as a Taylor series and after retaining the two terms of the Taylor series, we obtain the following. We obtain that delta B over B is approximately 1 over Br, and then I do a Taylor series expansion of B of R plus dr. So, this is going to be B of R plus dB dr into dr plus half d square B dr square into dr whole square minus Br, plus the higher order terms which I am neglecting, which is the reason why I have this approximation. So, this Br terms cancel out. So, we get 1 over Br into dV over dr multiplied by dr plus half d square B dr square into dr whole square. Now, once I have this expression, so this can now be written as delta b over b, and dv over dr is simply going to be minus d over 1 plus r. So, now what we have? We basically have this term dv over dr divided by br. So, this is nothing but minus d over 1 plus r multiplied by dr, plus we have half d square b dr square divided by br. So, this half term comes outside, and the remaining term, that is d square b dr square over br, this you would recall is the definition of convexity. So, this is c into my dr square, and this term here was used to define the modified duration. So, this can be written as minus dm into dr plus half c into dr square, and this of course is in the sense of approximation. So, in summary, what you can say is the following, that first of all, delta b over b is going to be approximately minus d over 1 plus r dr, and is equal to minus dm into dr when you are using only duration. And secondly, from this expression we get delta b over b, which is approximately minus dm into dr plus half c of dr square for both duration and convexity. So, that means that you can get an estimate of the percentage change in the bond price, and this is some sort of like this term here, this form is some sort of a first order approximation, and this expression here is some sort of a second order approximation. So, this percentage change in the bond price can in the simplest case be given in terms of the duration or the modified duration, and that means the percentage change is dependent only on duration. And on top of this, you can actually have a better approximation by the inclusion of the convexity term, wherein you accommodate that the percentage change of the bond price is dependent on both duration as well as convexity. So, this the first term where you only invest duration gives an estimate, and the one which second expression which involves the both duration and convexity, it gives us a better estimate as compared to the first case. So, in some sort of this addition of the convexity term helps us obtain a correction or a better estimate as compared to the one that is given by just the duration only, and this is estimation for what? This is the estimation for the percentage change in the bond price as a result of the interest rate moving by some small amount of dr. Okay, so now recall that d is equal to minus of 1 plus r over b into dv dr, which gives the following. So, I can take the derivative of this. So, dd over dr, this is going to be minus of b minus 1 plus r b prime over b square into b prime minus 1 plus r over b into b double prime. So, I am just using the product rule of differentiation. Also, you recall another form of this dd over dr, and that was given by dd over dr is equal to minus of 1 plus r inverse into vd. So, therefore, what do we have? So, we can equate both this expression for dd over dr, let me call this 1 and 2. So, therefore, equating 1 and 2, we obtain the following. So, we get that b of r minus 1 plus r b prime of r over b square r into b prime of r plus. So, this will become plus. So, there is a negative sign here and negative sign here, all of which will cancel out. So, I will have 1 plus r over b of r into b double prime of r is equal to 1 plus r inverse into V d. So, this implies that 1 over b of r into 1 plus d into b prime of r plus 1 plus r over b r into b double prime of r is equal to 1 plus r inverse into V d. So, essentially this term here is nothing but writing this term in a different form. So, the first term is going to be say b prime into b r over b square r. So, this is b prime r over b r. So, you see that this is b prime over b r and the other term will contain d, and the remaining two terms have been reproduced as it is. Alright. So, now what you can do now? So, now observe very carefully. So, I have this 1 plus d term and then I have b prime of r over b r, which is nothing but minus d over 1 plus r, and here I have b double prime of r over b r. So, this is going to be 1 over 1 plus r, and this term here is going to be c, and this is going to be equal to V d over 1 plus r. Now, this implies that minus d into d plus 1 and multiplying both sides by 1 plus r. So, I get plus 1 plus r whole square c, this is equal to V d, and this implies that c is going to be equal to 1 over 1 plus r whole square into, so I bring this term to the right hand side. So, I get V d plus d into d plus 1 and I divide both sides by 1 plus r whole square. So, now you see that we have a relation which connects the convexity with the duration. Alright. So, now what we have done is we have talked in detail about what is the definition of duration and as well as convexity. We also looked at what is going to be the duration and convexity of a portfolio of bonds, and in both cases this was seen that the respective quantities, namely the duration and convexity of a portfolio, is going to be the weighted sum of the duration and respectively the convexity of the each of the bonds that are a part of this particular portfolio. And what we did is that we then observed that this duration and convexity, they are basically some sort of a matrix in order to evaluate what is going to be the percentage change in the price of the bond whenever there is a slight change in the interest rate. And we saw that this, when the approximation to this percentage change was done using duration, this was some sort of a linear relation or linear function of dr, and when it was extended and to obtain a better estimate involving the convexity, then it became a quadratic function of dr, and these two were essentially two ways of approximating the percentage change in the price of the bond. So, what we are going to do next is we are going to look at a couple of examples on how one can make use of this notion of duration in case of immunization, and we will show first a generalized example and then we will look at a specific example to illustrate this notion of bond portfolio optimization, making use of the concept of immunization, which essentially relies on the matching of durations. So, accordingly, we first start with this generic example, and this example is on the problem of future assets and liabilities, and in particular we will dwell upon what is known as the Reddington's condition. Okay, so accordingly let us have the prelude to this. So, let the future cash outflows of an entity at time t is equal to 1, 2 all the way to capital T be denoted by capital L subscript T, L is for liability. Also, let the future cash inflows as opposed to outflows of the entity at time t is equal to 1, 2 all the way to capital T be denoted by say AT, and A is for asset. All right. Now, suppose that, so as has been the case so far, we also assume in this case that the interest rate term structure is flat. So, that means the interest rate for all maturities is identical. Then the present value of future liabilities and assets are given by the following. So, if we have the payments liabilities of LT at time t, so the present value of the tth liability is LT into 1 plus r raised to minus t, and then the present value of all this liability is going to be summation of this from t equal to 1 to capital T, which are denoted by capital L. And likewise, the assets at time little t, the present value of which would be 1 plus r raised to minus t into AT, and I sum this up from t is equal to 1 to capital T, and I will denote this by A. And the assumption is that the initial net value of future cash flows. So, I will use n is equal to A minus L. So, this is the net value, and this is 0 at the initial time. So, n equal to A minus L is the generic net value of future cash flows, and at the initial time point we take this to be equal to 0. So, initially we have A is equal to L. And the question that we want to answer is that how to choose the structure of assets so that this net value does not change as a result of change in interest rate. So, that means that this is unaffected by interest rate, and the broader answer to this is that we want, so this is equivalent to saying that we want that this net value n given by A minus L to be insensitive to R. So, when I say that we want this to be insensitive to R, so hence this means that we want that dn with respect to dr is going to be equal to 0. All right. So, therefore, what is going to be my dn dr? Dn of dr is nothing but the derivative with respect to r of A minus L, and what is A minus L? This is going to be summation AT minus LT into 1 plus r raised to minus t, t is equal to 1 to capital T. And this is nothing but, if you take the derivative 1 over 1 plus r summation t is equal to 1 to capital T, t into LT minus AT, because this the derivative of this will involve minus t. So, I change this sign and make this LT minus AT into 1 plus r raised to minus t. And what is this? This is going to be, if you observe carefully each of the term, you keep 1 over 1 plus r outside, and this summation t LT to 1 plus r raised to minus t, this is nothing but dl of L minus dA of A, where as you would have guessed, dl and dA are the duration of L and A. So, dl What is this going to be? This is going to be summation t is equal to 1 to capital T, by definition is t into L of t into 1 plus r raised to minus t over L. So, here this term t L t into 1 plus r raised to minus t, this is going to be this term here, and that is d L of L, which is how I get this term here. And in identical manner, the duration of the assets is going to be summation t A t into 1 plus r raised to minus t over A, and t is equal to 1 to capital T. So, again this term is the one that we have here, and accordingly this term is going to be dA into A that we obtained here. Now, remember that this what we have. So, this is simply going to be A over 1 plus r into dL minus dA. Since my A is equal to L initially, and this has to be equal to 0. Remember that we need d and dr to be equal to 0, and this is the, therefore, we need that dL is equal to dA, so that we are going to have a matching of our assets and liabilities. Okay, so next we look at another example, the last example, and this is on hedging using immunization. So, here let us have the problem set up. So, let us assume that the term structure is horizontal, and let the annual interest rate be 5%. So, that means there is a 5% interest rate for all maturities, because I have assumed that term structure is horizontal. Now, suppose that we have a liability of 100 with maturity of 2 years. Now, in the market, suppose there are two bonds, namely the first one is a pure discount bond of maturity 1 year with the nominal of 100, and secondly there is a pure discount bond of maturity 4 years with the nominal of 100. So, let us observe this graphically. So, what you have is that on one side you have the liability, that means from now to 2 years, at 2 years you have to pay an amount of 100, and accordingly and then what you will have is that in the market there are only two bonds. The first bond is of maturity 1 year with a nominal of 100, and these are pure discount bond, and the second one it has a maturity of 4 years with a pure discount bond. Now, what am I supposed to do here? I mean, why am I calling it the hedging? The reason why I am calling it the hedging is that I have a liability of an amount of 100, and as I will shortly write that I start off with an amount of 90.70. Now, if it turns out that the market had a 2-year bond available at the interest rate of 5%, then all I would do is simply invest the money that I have now, that is an amount of 90.70 for a period of 2 years, and at the end of 2 years I will exactly get an amount of 100 in order to meet my liability. However, in the market unfortunately there is no 2-year bond, and the only thing that I have in the market are 1-year bond and there is a 4-year bond. Both are pure discount and both of them have a nominal of 100. So, now the problem is that if I invest a part of my money in the first bond for 1 year, then at the end of 1 year I have to reinvest that money, and then I do not know what is going to be the prevailing interest at that point of time. And likewise, I have to invest a certain amount of money in the 4-year bond, which I have to liquidate or break at the end of 2 years, and again I do not know how much money I will receive, because the amount of money that I receive at the end of 2 years by breaking the bond is going to be dependent on what is going to be the prevailing interest rate at that point of time. So, the question that now faces me is that since I do not have, I am sitting with an amount of 90.70, and since I do not have the choice of buying a 2-year bond, and then I have to decide that okay, I will have to go for a portfolio of bonds comprising of the first bond with a 1-year maturity and the second bond with a 4-year maturity. So, let me call this the first one to be bond 1 and the second one to be bond 2. And the question is that how much of the initial amount of money that I have, namely 90.70, as that amount of money, what proportion should I invest in the first bond with 1-year maturity, and what proportion or the weight that I should assign in case of the second bond with the 4-year maturity. So, let me call this bond 1 as I have just now said, and this is going to be my bond 2. Okay, so now as I mentioned while discussing this just now, we start with an amount of 90.70. So, if we have 90.70, if we had a 2-year bond, this into 1.01 plus 0.05 square, this would have gone to 100. But unfortunately, this kind of bond is not available, and so I have to create a portfolio of bond 1, that is this bond, and bond 2, that is this 4-year bond. All right. So, now in order to meet the obligation of 100 in 2 years time, we have to invest in a portfolio of bonds by immunization, or what is known as matching duration. So, we have already seen that the duration matching has to be done. So, this means that in order to put this in more specific term, what we say that is one liability with maturity of 2 years must be matched with by purchasing of bonds of maturity of 1 year and 4 years. Now, the liability after 2 years has duration of 2. Now, why am I saying the liability after 2 years has a duration of 2? So, liability of this 100 that you have to pay after 2 years, this is like you having issued a bond of with the nominal value of 100, and the bond is a pure discount bond. So, you recall that one of the properties of a pure discount bond in terms of duration is that in case of a pure discount bond, its duration is going to be exactly the same as the maturity of the bond, and that is the reason why that the liability of this 2-year liability of an amount of 100 to be paid at maturity, that liability is equivalent to a bond having a duration of 2. So, accordingly, whenever I try to protect myself against the adverse movement of the interest rate, so in this case the bond portfolio that I am going to create, it has to be created in such a way that the duration of the bond portfolio has to exactly match this duration of 2 years. That means, I must choose my investment proportion or weights for bond 1 and bond 2, so that the resulting duration of the bond portfolio is going to be the same as 2. So, accordingly, so what is the goal? So, just to put it in more clear term, that the portfolio of bonds must then also have duration 2. So, let the weights of the 1 year and 4 years pure discount bonds, that is the one which are identified as bond 1 and bond 2, this be alpha and 1 minus alpha respectively. The corresponding duration, now remember that both this 1 and 4 year bond, these are pure discount bond. So, the corresponding duration are d 1 is equal to 1 and d 2 is equal to 4. So, then we do this matching duration, and what is this going to be? It is going to be the weight of the first bond into duration d 1 plus weight of the second bond into duration d 2, which is equal to the duration of the portfolio, which is equal to 2. So, this implies that alpha into 1 plus 1 minus alpha into 4 is equal to 2, which implies that alpha is going to be equal to 2 over 3. So, that means you have to assign 2/3 weight to the first bond and 1/3 weight to the second bond. So, therefore, what do? We invest. How much was the investment amount? My investment amount was 90.70, and I invest 2/3 of this amount, and this is going to be 60.47, and this is my investment in bond 1. And similarly, you will have the remaining 1/3 of the total amount of 90.70. So, this is 30.23, this is invested in bond 2. Alright. So, based on the weight, 60.47 is invested in bond 1 and 30.23 is invested in bond 2. Now, what is the price of the bond? So, price of bond 1, how do we get the price of bond 1? It is basically the price of the bond 1 is equal to, it pays a nominal of 100, and since it is a pure discount bond paying interest rate at 5%. So, I have to divide this by 1 plus 0. So, this is 1 plus 0.05 raised to 1, because it is a 1 year bond, and this is 95.24. So, therefore, N1 is going to be equal to 60.47, that means the number of bonds that you purchase is the amount invested in the bond, which is 60.47, divided by the price of the bond, which is 95.24, and this turns out to be 0.63, and this is the units of bond 1. Now, also, what is going to be the price of bond 2? Now, remember, the bond 2 also has a nominal of 100, and this was a 4 year bond at an interest rate of 0.05, or that is 5%. So, this is going to be 100 divided by 1 plus 0.05 raised to 4, since it is a 4 year bond, and this turns out to be 82.27. So, therefore, N2, what is N2? The number of units of the second bond. This is going to be the amount of 30.23 invested in the second bond divided by the price of the second bond, which is 82.27, and this is going to be 0.37 units of bond 2. And please do not assume that the number of units must add up to 1, even though in this case coincidentally N1 plus N2 adds up to equal to 1, but it is obviously not necessarily the case. Alright, so what is now the purpose of my matching duration? The purpose of my matching duration is to protect myself against the interest rate movements. So accordingly, let us consider two scenarios of an immediate change in the interest rate movement. So the first scenario is going to be the following. So immediately after you have made these purchases, say the rates go up from 5% to 6%, but of course, I still assume that the term structure is horizontal. So this means that earlier we had a 5% interest rate for all maturities, now it is 6% for all maturities. Then what is going to be the present value of assets and liabilities are given by. So what is this going to be? So what is going to be your assets? So actually let me do the liabilities first. So the present value of liabilities and assets are. So what was your liability? Your liability was 100 and its present value, since it is an immediate change in the interest rate, so its present value is going to be 100 divided by 1 plus 0.06, because the interest rate now is 0.06 square, and this is equal to 89. And in the second case, what is going to be the present value of bond 1? It is going to be 100 divided by 1 plus 0.06 raised to 1 and 100 divided by 1 plus 0.06 raised to 4 multiplied by the respective units, which are 0.63 and 0.37, and we add this up and this turns out to be 88.74, and these two numbers, these match approximately. So they should have similar. So earlier these values were 90.74, but now they are almost matching, with a slight error resulting from the truncations resulting from the approximation used in determining the duration. Now, so this matches approximately. Then you would consider what is the scenario 2. So now here we saw that there was an increase in the interest rate. So let us consider a scenario 2 where there is a decrease in the interest rate. So the assumption is that immediately after the rates go down from 5% to 4%, but as before, the term structure is still horizontal. So now instead of 5% being the interest rate for all maturities, it is going to be now 4%. So in this case also, the present value of liabilities and assets are the following. So in this case, your liability again you recall was 100, and then its present value is going to be 1 divided by, now the interest rate is 0.04, which is equivalent to 4%. So the liability is going to be, present value of the liabilities 100 divided by 1 plus 0.04 square, and this is going to be 92.46, and 100 divided by 1.04 is going to the present value pertaining to the first bond, and 100 divided by 1.04 raised to 4, this is going to be the present value of the second bond, and then I multiply this by the respective number of units, which are 0.63 and 0.37, and I add them up, and this adds up to 92.20. And again you see that there. So earlier again this both these numbers, this number here and this number here, they were 90.70, but now again they are more or less matching approximately. So, this brings us to the end of this lecture and this topic on bond portfolio optimization. So, just to do a recap of whatever we have done today, we continued our discussion on by extending the notion of duration, and you extended it to a second order matrix for determining or which is linked to the risk associated with the bond, in particular the liquidity risk, and we defined what is known as the convexity. And then we looked at what is what is going to be the convexity in case of a portfolio, and we looked at approximations to the percentage change in the bond price as a result of interest rate movement in terms of both duration and convexity. And then we looked at two examples illustrating the notion of immunization or matching of durations. So, this, as I said, concludes this module on bond portfolio optimization, and from the next week we will start off on the new topic, that is on risk management using the notion of value at risk and conditional value at risk. Thank you for watching.